In this video, we're going to be doing some mathematics from this book. This book is called Differential Equations and the Calculus of Variations, and it was written by Elgolts, Moscow MIR Publishers. The mathematics that we're going to do involves a derivation, and then I'm going to do an actual example after I do the derivation. But first, let's just take a look at this book so you can see what this book is about. Differential Equations and the Calculus of Variations, translated from the Russian by George Yankovsky, MIR Publishers, Moscow. The subject of this book is the theory of differential equations and the calculus of variations. It is based on a course of lectures which the author delivered for a number of years at the physics department of the Lomonosov State University of Moscow. Cool. Let's just take a brief look at the contents, and then we'll jump into some mathematics. So the first part of this book is differential equations, and these are topics that you would study if you were to take a differential equations class in college. The mathematics we're going to do in this video is from this first chapter. So if you're taking differential equations or you know some calculus, hopefully you can follow along. And then part 2 is on the calculus of variations. Pretty cool stuff. Answers to problems, page 429. You can see here that the book has answers to all of the exercises, which makes it pretty good for self-study. Now, I've read portions of this book, and I think it reads quite well. If you have some calculus background, you should be able to read this book and learn from it. Some of the techniques and some of the explanations in this book are a little bit different than the explanations that you would see in a more modern book. And that's why I thought it would be really cool to do some mathematics from this book and show you some cool math. So let's go ahead and jump into it. We're going to start with a derivation, and feel free to skip ahead to the actual example, but it's just kind of fun to see how things were taught in a different era. Okay, let's jump into the mathematics right away. So the setup is that we have a differential equation, dy dx, plus p of xy, and it's equal to f of x. And this is a first-order linear differential equation. So if you go to school or if you buy a book on differential equations, you learn about this, and they give you a method for solving this. So what I'm going to give you in this video is another method. So we're basically going to do the abstract version of the method, and then we're going to do a specific example of the method. So this is the abstract version. We just have functions p of x and f of x and y. So we'll start by solving what's called the homogeneous differential equation. That basically means we set this equal to 0. So we get dy dx plus p of xy equals 0. Okay, so basically we just set that equal to 0. And this differential equation is actually easy to solve once you know how to solve differential equations. This is called a separable differential equation. So basically you want to get all of your x's on one side with the dx and all of your y's on one side with the dy. So I'm going to subtract this over to the other side. So minus p of xy minus p of xy. So we get dy dx equals minus p of xy. And so now we want to get all of the y's on this side because the dy is here. So I'm going to divide by dy, so we get dy over y, and then multiply by dx, so we get negative p of x dx. Now we integrate both sides. This is a familiar integral. If you know some calculus, this is the natural log of the absolute value of y. And this is just this, right? We don't know what it is, so I'm just going to pull out the negative and write it like this. And since we integrated this, I'm just going to go ahead and I'll add the constant here, plus c1, just like that. All right, so now we're going to exponentiate. I'm going to put an e here, put an e here. This is really in parentheses here. And so this goes away, right, because there's that powerful formula, e to the ln x is x. That's because e to the x and the natural log of x are inverse functions, and so when you take the composition, you get x. Basically, they cancel. This is the absolute value of y equal to, this simplifies to the following, or rather, can be written in the following way. Minus integral p of x dx times e to the c1, okay? And the reason it's that is because when you multiply these, because the bases are the same, you add the exponents. When you drop the absolute value, you get a plus or minus. I'm going to bring this guy here to the front. Okay, so we get that. And then let's just rename this. I'm going to call it C. So I'm just going to call this C. So we have, I'm just going to come over here, y equals C times e to minus integral p of x dx. So this is the solution to the homogeneous equation, right? The homogeneous equation. When you study higher order differential equations that are linear with constant coefficients, they call this the complementary function. So what we're doing here is very similar to what's done in higher order differential equations. So if you study those, or if you know what I'm talking about, you understand. If not, don't worry. So this is the solution to this. So now the issue is, how do we find the solution to this, right? So what we're going to do now is pretty messy. I think I'm going to have to get a different sheet of, well, I'll continue with this paper. So we're going to make a change of variables. We're going to assume that c is a function of x. So we're going to let y be equal to c of x times e to the negative integral p of x dx. And then basically what we're going to do is we're going to take the derivative of this and plug it into our differential equation up here. So let's go ahead and take the derivative using the product rule. Okay, recall the product rule. Let me just write it here for you. If you have f and g and you take the derivative, think of f as your first function and g as your second function. So it's the derivative of the first times the second plus the first times the derivative of the second. Okay, so here, this is going to be our first function and this is going to be our second function. You might say, how are we going to differentiate that, right? We'll do it, no worries. So dy dx is going to be equal to the derivative of the first, which is c prime of x, we don't know what that is, times the second, which is e to the minus integral p of x dx, plus the first, c of x, times the derivative of this. Well, the derivative of e to the x is e to the x, right? But here it's e to all this stuff, so it's e to all that stuff, times the derivative of the inside. So the negative hangs out. When you differentiate the integral sign goes away. You just get p of x, just like that. Right? Really cool. All right, so we can put this in the front here. So dy dx, okay, is equal to c prime of x, e negative integral p of x dx, minus, and then I'll just go ahead and put the c of x here, the p of x here, and then here we have this e to the minus integral p of x dx. Okay, so that's going to be the derivative. So now we just have to take this and plug it into our dE. I'm going to get another sheet of paper and we'll continue. Okay, I am back and I have a sheet of paper and here we have everything summarized. So let's go over it again before we continue. So this is a first order linear differential equation and we started by setting f of x equal to 0. In other words, we have the homogeneous version of this equation. We solved it and we got this as the solution to the homogeneous equation. So then we said, hey, what if c was a function of x? Let's do that and plug it into this dE to see if we can come up with a solution. So we did that, we called it y, and then we took the derivative. So now we're going to plug it into the dE. So I'm going to write all this again. So dy dx is this, I'm going to write it, c prime of x, e to the minus integral p of x dx, minus c of x, p of x, e to the minus integral p of x dx, plus p of xy. But what's y? Y is all of this, right? So now we have to replace the y, right? This y gets replaced with this. So it's going to be c of x, e to the minus integral p of x dx, and this is equal to f of x. So this is really cool because look, boom, right, really nice. We get some cancellation. So now we have c prime of x, e to the minus integral p of x dx, and that's equal to f of x. Okay, so let's solve for c prime, because if we can get c, we're good, right? Because we have y, we already know this part. But what's c? Can we come up with a formula for that? So I'm going to divide by this. Okay, so we get c prime of x equals f of x over e to the minus integral p of x dx. And this is going to seem weird, but basically when you bring this up, the exponent becomes positive, right? That's the exponent, that integral there with the negative sign outside of it. So this will become f of x e to the integral p of x dx. So now we're going to integrate both sides of this equation, right? So then c of x is equal to, okay, it's going to be the integral of f of x times e to the integral of p of x dx, okay, plus some arbitrary constant, which I'll call it c sub 1. Really cool. So now what we're going to do, I'm just going to put this in a box. Okay, now we're going to take this, okay, and we're going to plug it back in here, okay? So let's do that. So I'm going to write this piece down here so you can see it. So we have y equals c of x e to the minus integral p of x dx, okay? And that's going to be equal to, well, c of x is all of this, right? So parentheses, integral f of x e integral p of x dx plus c1. All of that's being multiplied by this. So this is e negative integral p of x dx. Let's distribute. So this is equal to, so I'm going to write this one first, okay? So c1 times this, I'm going to put it over here. c1 e to the minus integral p of x dx. This is y. Okay, this is the solution to the dE. And then this one, I'm going to put it in front of this just so it doesn't look so messy. So it'll be plus this e minus integral p of x dx times the integral of f of x. And inside the integral, we have an e and another integral as the exponent, dx. So this would be the solution to the differential equation dy dx plus p of xy equals f of x. So in practice, it's not a good idea to use this formula. I mean, you could, just like in theory, you could memorize the formula, right? But it's probably not a good idea. And so this is interesting because this is the homogeneous solution. And this is like the non-homogeneous solution. So the solution is the sum of the homogeneous part and the non-homogeneous part. And that mirrors what happens later when you study higher order equations. That's how it's taught. So a different way to explain the process. So now we're going to take this method and we're actually going to solve a differential equation. So we're actually going to basically repeat the procedure but with actual functions so you can see how it works. So let's go ahead and do that. Before we do the example, let me just explain a small little detail that I failed to mention, and it's not a huge deal, but it's worth knowing, and I think it's worth mentioning. So here we were solving the homogeneous differential equation. We set it equal to 0, and notice here that we divided by y. So when you divide by y, that means that y can't be equal to 0, right? And then when we got here, I called this c, okay? And so we have this. But notice that c is equal to this, right? So c can't be 0. So therefore we're saying basically that y equals c e to the negative integral p of x dx. We're saying that this is the solution to this differential equation, which it is, but it's not all the solutions. And that's because y equals 0 is a solution, because if you let y be equal to 0, the derivative is 0. So it's going to be a solution to this differential equation. But this doesn't allow y equals 0 because c is not 0 because of the nature of the exponential function, right? And plus, we divided by y, so we're not allowed to have y equals 0. So if we just be bad for a moment and say, hey, you know what? We're going to allow c to be 0, despite this condition, then this will give us all of the solutions to this homogeneous differential equation. And so whenever you have all of the solutions like this in a formula, it's called the general solution. Anyways, small technicality, small detail. Let's go ahead and jump into the actual example. Okay, so here is our example, and it's not a particularly hard example, but we're going to apply the procedure we just did to this actual problem. So the first step in this procedure is to solve the homogeneous equation, so solution. So we have dy dx minus y over x equals 0. And so we know that this is separable, so basically I'm just going to add this over to the other side. So this implies that dy dx is equal to y over x. So we'll divide by y, multiply by dx, right? So that's going to give us, dividing by y, we'll get dy over y. And then multiplying by dx gives us dx over x. Now we can integrate both sides. So we have the natural log of the absolute value of y equals the natural log of the absolute value of x plus some constant, which I'll call k. Exponentiate both sides. There's a parentheses here. So this is e to the natural log absolute value of y equals e to the natural log absolute value of x times e to the k. Again, this whole thing is the exponent, and because the bases are the same, when you multiply here, you add the exponents. So we get some cancellation, so we get absolute value of y equals, let's put the e to the k in the front, times the absolute value of x. So here we can drop the absolute values, we get a plus or minus, and then e to the k times x. Let's go ahead and call this c. So now we have y equals c times x, and that's going to be the homogeneous solution. So this is the homogeneous solution. So it's the solution to this differential equation. So as before, to find the solution to this differential equation, we're going to assume that c is a function of x. We're going to take the derivative and plug it in. So let's do that. So we're going to let y be equal to c of x times x. And so the derivative will be dy dx. Using the product rule, it's the derivative of the first times the second plus the first times the derivative of the second. I'm going a little bit faster here. If you made it this far, it means you probably made it through the derivation, so this should be easy compared to the derivation. so I'm going to write this again because it looks kind of messy. C prime of x, x plus c of x. And actually, I'm going to sharpen my pencil because it's starting to feel dull. I think the sharp pencil will strengthen my mathematical skills a little bit more. Yeah, this is a faded, it's a faded Ticonderoga. All right, so now we're going to plug this into the dE, which was this, dy dx minus y over x equals x squared. So now plugging it in here, we get c prime of x times x plus c of x minus, and then y is c of x times x, and then here we have x. So basically, we just took this, okay, and we put it here, right, because that's dy dx, minus y, which is here, so that went there, okay, and then over x, and that's equal to x squared. All right, so what happens here? These cancel, so you get c prime of x times x plus c of x minus c of x equals x squared. Let's cancel. So c prime of x times x equals x squared. Divide by x, so you get c prime of x equals x. Integrate both sides, c of x equals x squared over 2 plus a constant, which I guess I'll call c1. All right, so now we have c of x, and we know we have this here, so we can just plug it in, right? We get our answer, so we put this here. So we'll have y equals, let me zoom in so you can see here. So actually, let me zoom out so you can see what I'm plugging in. So I'm going to plug this in here. So we have c of x, so I'll write it again. C of xx. C of x is this, so it'll be parentheses x squared over 2 plus c1 times x. So multiplying here, we're going to get x cubed over 2 plus c1x, okay? And that is actually the answer. That would be it, right? So that's going to be the solution to the differential equation, which we had originally here. So interesting method. Basically, zoom out a little bit. There we go. So you can see So just a recap of the procedure, right? You basically set it equal to 0. It becomes separable. You solve it. And then you assume that your constant is a function of x, differentiate, plug it in, and then just solve for c of x, and you have the answer. So very different from the way that is taught in most books. So I thought I would just share that with you. So kind of cool. I did forget to mention one thing in the derivation. So if you're still with me, let me just find my work here. There was a part somewhere where we divided by, how many pieces of paper did I use? By y, and so y couldn't be 0. So I think it was when we were finding the homogeneous one. Let me see if I can find it here. It's a bit of a mess. So if you made it this far in the video, that's pretty amazing. That was a lot of math to get through. Hopefully you understood some of it, and hopefully you've enjoyed this video. I hope this video has been helpful to someone. Good luck.